Sounds good. Thank you. So my name is Eric Wright. I'm from the University of Delaware. So I'm going to be presenting my work towards porting an application called MURaM to GPUs using the programming model OpenACC. I also want to briefly shout out some of the collaborators that have also contributed, and continue to contribute to this project. My advisor is Sunita Chandrasekaran, also from the University of Delaware. Then we have some folks from NCLAR. Some of them have talked in the past hour or so. Sina Miller, Sabrit Suresh, Shaquan Su, Matthias Rempel, and Richard Loft. And then joining us from Germany, we have Damian Shabilsky from the Max Planck Institute for Solar System Research. So a quick outline of what I'm going to be talking about. I'm going to first introduce what MURaM is and our goals specifically with this project for MURaM. I'll talk about some of the workflow and tools that we've used, and then I'll focus the majority of the talk on how we have optimized our radiative transfer solver, which is a very significant portion of the computation in MURaM. And then I'll wrap it up with our results so far at this point in the project. So MURaM is an application for simulating the various layers of the sun's atmosphere. It was jointly developed by HAO, the Max Planck Institute for Solar System Research, and the Lockheed Martin Solar and Astrophysics Laboratory. The future goals that we have for MURaM are kind of the driving force of this project. There's a telescope called the DKIST telescope. It's a solar telescope that is currently being built in Hawaii. And once it is finished, we are expecting unprecedented or new high resolution images of solar phenomena. And to accommodate for this higher resolution data, we're looking to get about a 10 to 100 times performance increase in MURaM compared to the current baseline. And this increase in data resolution and computational power is kind of pushing us towards an exascale supercomputing problem. We also have the motivation that right now MURaM is about 10 to 100 times slower than real time. So one goal for this is also increase the performance to try to bridge that gap to either achieve real time or surpass it. So I like to refer to this project as MURaM GPU because MURaM is a traditionally C++ MPI CPU application. But the recent trends in high performance computing and supercomputing has really pushed that GPU programming is more or less the way to go. For example, in the Summit supercomputer that's in Oak Ridge National Lab in Oak Ridge, Tennessee, they have 6 GPUs for every node of their supercomputer for a total of over 27,000 GPUs for the entire machine. So in order to be able to accomplish our science goals, going the GPU route for these kinds of supercomputing machines seems to be a very good route. So for our program model of choice for GPUs, we've chosen OpenACC. So OpenACC is a directive-based parallel programming standard. So some of the benefits of OpenACC for this specific project is that we're able to have one source code that can be built or compiled for either CPU or GPU, so we don't have 2 separate Git repositories or anything like that. We can just work from one source code and do both, because there will still be some users of MURaM who will run the CPU version or don't need GPU acceleration for their work. It also allows us to do incremental parallelization of the code. So since this is a large source code, we don't really want to rewrite it in a completely separate language. It's a lot of changes to make at once. We can make a small change, run it, test it, and then make another small change until we're happy with it. Some other projects that I have listed here, the MOM6 and the MPAS project were actually talked about in the previous 2 talks. Some of the people who have actually done work for these 2 projects was Sina Miller and Sabrit Suresh, who had talked at the beginning of this period, if you're around for their talks. So one of the main tools that we use when we're developing our GPU code is a GPU profiler. Specifically right now, we're using the NVIDIA Visual Profiler, or NVProf. This allows us to look at each GPU kernel that we're writing and to kind of do a deep dive on how that kernel is performing, how it's utilizing the GPU hardware, and things like that. But then we can also look at how various GPU kernels are interacting, the overhead between them, the data movement between them, and things like that. whenever we make a change to the code, we kind of go back to the profiler and we see, did the change work the way we expected? What are the remaining problems we still have to address, and things like that. One metric that you can get from these kind of profilers that we have used quite a bit is GPU occupancy. So GPU occupancy is the ratio of the GPU compute resources that you're using divided by the total number of available resources on that device. There's two different measures that we're really using here. There's achieved occupancy and theoretical occupancy. Achieved occupancy is observing the code when the code is actually running. So this is something that you could do with the profile. And it kind of gives you a sense of, okay, when I'm actually running this kernel with whatever data I gave it, how much of the GPU am I actually using? And then theoretical is based on the compiler, essentially. So when you compile the kernel, how many resources are being assigned to it will determine how much of the compute resources you're actually able to take advantage of. So I have a chart here with a few different kernels from MURaM and their achieved and theoretical occupancy. And this measure has kind of shown us two very different but important problems that exist within MURaM. So the first problem is seen within the MHD, TBD, cons, and Interpol kernels. And that is that the theoretical occupancy, so what our theoretical peak is, if all the stars align, is really low. For MHD and cons is only at 25%. So best case scenario, we're only using about 25% of our compute resources on the GPU. And because of that, the achieved occupancy is also suffering as well. So it's only achieving 25% as well. I'm not going to talk about this problem for this talk, just for time reasons. But essentially, we're working on rewriting code to try to get the compiler to use less shared memory and registers and things like that to try to improve the theoretical occupancy, and hopefully the achieved will increase with it. The second problem, and the one that I will talk a lot about, is seen with integrate and to a lesser extent in flux. This is where the theoretical occupancy is ideal. It's at 100%, that's where we want it to be, but when we're actually running the code, we're not achieving our theoretical max. And in terms of integrate, we're only achieving 11% of our theoretical max. So this problem where we're not really achieving the occupancy that we theoretically could is what I'm going to be discussing for most of this talk. So I'm going to talk about the radiative transfer solver, or RTS, from here on out. This is a very important portion in MURaM. We're doing a three-dimensional radiative transfer solver. Sorry, I kicked a wire on my computer and my screen started flickering. Sorry about that. We're doing a three-dimensional radiative transfer solver. And for the entire MURaM application, RTS is taking the most time out of everything. There's a lot of things happening in RTS, but RTS in general is taking the most time. And within RTS, we have one kernel in particular that stands out above the rest. That is the integrate kernel, which was in that occupancy chart on the last slide. Integrate must be run at least 24 times per time step. It must be run at least once for each of the 24 arrays. So array is a combination between an octant and an angle. So in our 3D space, or our 3D domain, we have 8 octants, so each angle of our 3D space. And then at each octant, we're doing 3 different angles for a total of 24 arrays. You have to do at least one integrate for each array, but depending on how long it takes to converge, you might need to do more. So you're probably looking more in the ballpark of 50 to 100 integrates per time step. Integrate also introduces a data dependency. It's called a wavefront dependency. So we have to be very careful when we parallelize it, or else we're going to get very incorrect results. I just kind of want to explain what the dependency looks like to visualize it. So we have this 3D cube. Each kind of like piece of the cube, you can think of it as one point in our 3D space, or like a grid cell. Before integrate starts, we have these boundary conditions. So all these gray grid cells are predetermined before integrate even starts. And then we can go through and we can compute all of the red grid cells in parallel. So we could have a parallel loop that computes them all simultaneously. That is fine. However, before we can compute the blue grid cells, all of the red has to finish prior. So we have this kind of sequential ordering where we do the red grid cells And then after they finish, we can do the blue. And then finally, after the blue finishes, we can do the green. So we kind of are taking a 3D space and dividing it into two-dimensional parallelizable slices. So there's two problems in integrate. The first problem is that the outermost loop of this kernel has to be sequential. We have to keep a sequential order over those two-dimensional slices. Because of this, instead of launching just one kernel, we're ended up launching hundreds every time we call it integrate, which is not great, as it introduces a lot of kernel launch overhead and things like that. And because we're only parallelizing two dimensions of our problem, these kernels are really small and really inefficient, which we can see from the profile here. These blue rectangles are the computation for integrate happening on the GPU. You can see that the time spent computing our answer is much smaller than the time gap between kernel launches. So the overhead of launching the kernels is more time consuming than actually doing the computation. And then the second problem is that because of the data dependency in integrate, we have three different kind of dependency patterns we can experience depending on the direction that ray is sweeping. So in dependencies in the Z direction, so if you're like doing the 2D slices in a Z direction, that is several times slower than the other two because of GPU memory reads and writes. So from the two profiles, the top one is a Y dependency pattern, which is taking 9 milliseconds per call to integrate. And then the Z pattern, we're doing 30 milliseconds, so over 3 times more. And this is a pretty ideal scenario. This data set I'm profiling here is not as bad as many others. Okay, so I want to introduce 4 different approaches or 4 different methods that we have tried to optimize integrate. They're all very different. They all have very different goals, or I guess very different implementations. The first one is to use GPU asynchronous programming. In OpenACC, this would be the async clause to put into an OpenACC queue. So we're doing 24 rays. The idea here is since each ray is only taking about 10% of the GPU's compute resources, we would put them all in their own separate asynchronous queue and try to get the GPU to overlap them or just do multiple rays simultaneously with the extra resources that it has. In theory, this sounds pretty good because we get to do 24 rays simultaneously, but in practice, we can't actually guarantee that that would happen. You don't typically use async for this kind of behavior, but it is possible. And we tried it, we ran it, we profiled it. And while there was some overlap happening between the different rays, it wasn't very significant. And on this chart, this chart's gonna come up a little bit, so I'm gonna explain it once. On the y-axis, that is the speed up of the whatever implement or whatever method I'm talking about compared to a baseline parallelization of integrate. And then on the x-axis is how large the data set that we're testing. And we're only timing integrate, we're not considering the rest of the code. So this is just timing that kernel. And we can kind of see that for the larger data set, so 256 cube, 192 cube, we're getting 1x speed up. So it's about equivalent to our baseline. And it isn't until we get really small at the 64 cubed where we're actually seeing a significant benefit. So this would only be really a way we'd want to go with the code if we were committing to doing those smaller data sets. The second method is to essentially take the computational work from a separate function. This function is called interpolation or Interpol. And we're taking the work being done in that loop and we're kind of merging it with integrate to essentially do both those functions or both those kernels within the same loop. And the goal for this is that each kernel is doing more work to hopefully achieve more occupancy and keep the kernel busy longer so the overhead is less impactful. But the downside of this is that Interpol will actually have to compute the interpolation more frequently. Normally you only interpolate once per ray, but since you might have to integrate multiple times, depending on when it converges, now you might also have to interpolate multiple times. And for this method, for the smallest data set, we saw a little bit of improvement, but that's not amazing considering that for the larger data sets, we're actually seeing a performance degradation. We're seeing it get slower. The third approach is to This is actually solving the second problem with the slower Z dependency pattern, and this is to transpose various arrays that are used and integrate so that the Z dependency pattern can have better memory reads and writes. So before this change, this little diagram here, the first one is the memory read and write patterns if you have an X or a Y dependency pattern. So you're reading from memory in a sequential order, it's all right next to each other, it's in perfect stride, which is great for a GPU, that's ideal. But then when you hit the Z dependency pattern, it doesn't have that. It has to kind of bounce all over the place and do a bunch of skips. And for a GPU, that is very bad for performance. It's one of the worst case scenarios for performance for a GPU. So essentially what we ended up doing is we took the arrays that we're using to integrate, we transpose them into a different order ahead of time, and that way the memory reads and writes can happen in a better fashion for the GPU. The main downside of this is that you have to do a little bit extra work up front, but it makes integrate faster as a result. And our speed up overall for integrate, so this is also actually considering the time it would take to transpose as well. The speed up overall for this method is pretty good across the board, and it's actually the first one that's good for the larger data sets. And then the last approach is to take arrays that have a similar dependency pattern, so if they are both going in an X dependency pattern, and to combine them with a loop. And the significance of that is that in OpenACC, if I have a loop over it, I can parallelize that loop. It's kind of similar to the asynchronous approach, but I'm actually verifying that it will be parallelized. The downside of this is that the algorithm becomes a little bit more complex, like how we determine convergence has to change a bit. So the algorithm definitely works a little bit differently. So that's something to consider when we're working on this. But the speed up for the smaller data sets, so 128 cube and 64 cube, ends up being pretty good. So this is a method that this and the transpose for us are looking really promising because we're seeing good speed up in some of the cases. So I'm going to go into the results and then I'll just go into questions. So the experimental setup that we're running on 2 machines from NCAR. They're called Cheyenne and Casper. Cheyenne is a completely CPU-based machine, whereas Casper has V100 GPUs. And for the compilers for this, we're using Intel 2019 for our CPU runs and PGI 19.10 for our GPU run. So we haven't migrated to the PGI 2020 version yet as of this presentation. So this chart is speed up of the entire MURaM code broken down a bit by kernel. With a single V100 GPU on Casper compared to a fully subscribed CPU node on Cheyenne. And essentially what we're seeing right now is that comparing 1 GPU performance versus 36 core CPU performance, we're seeing some things that are extremely promising for us, especially with us working on this, we kind of see these numbers improve over time, and it's really nice to start to see like it actually come together. But in total, we're seeing about 2x performance overall, which is pretty nice for us, especially considering that this is only a single GPU. We're not actually using all the GPUs on the node for this chart. RT, which is something we've worked a lot on, is getting up to 4x, which is for us is really awesome. The functions here, or the kernels here, that are like 100x plus, I would say that these are not very impactful to the overall performance because these kernels specifically are mostly MPI bound. So single GPU doesn't really have to do much MPI communication versus a full 36-core CPU. So while these numbers look great, it's not really very meaningful in this comparison. And there's other things that we can obviously improve on, and that's kind of the direction we're moving, looking at what we've done and what's left to improve on. Last bit of results is some strong scaling for going from single GPU up to 4. So I have on the x-axis 1 GPU, 2 GPUs, and 4 GPUs. And on the y-axis, I have the runtime per time step, and that's in seconds. And I also have the kind of 3D decomposition for the GPUs. So for example, this bullet here is a 2 by 2 by 1 decomposition for how we divide up all the grid points to our 4 GPUs. And for strong scaling, when we're looking at our best runtime decompositions, moving from 1 GPU to 2, we're seeing about a 2x speed up. It's actually closer to 1.95, but fudged it, which is really good for strong scaling. It means that the MPI overhead we're experiencing from scaling up isn't killing us yet. And then moving from 2 to 4, we're seeing a 1.8x speed up, which is still pretty good considering these are things are still being optimized, is still very much work in progress, but we're getting to a point where we're getting really happy and really excited for the potential. I'm gonna leave it on the summary slide, but that's the end of the presentation. I'm going to answer any questions that anyone has and anything like that. I want to thank everyone for listening, for taking the time out, wherever you are, to listen.
Okay, well, thank you, Eric. And let's see, do you have questions on your Slido? Or is, oh. Could you comment why higher return for optimizations is seen for smaller problem sizes?
Yeah, so this would be in terms of the integrate kernel and some of the optimizations that we did to that resulted in higher performance for smaller sizes. Some things to keep in mind, I would say, so I guess the big answer is that we're working on it, we're profiling it, we're trying to figure out exactly why. But the general consensus for me is that when you have a smaller data size for this specific kernel, those little two-dimensional slices that we have to parallelize get really small and really inefficient. So something like merging interpolation and integration, which ends up doing a lot more work, ends up being better for that small data size because it's at that point it's just extremely inefficient for the GPU. So I think it just comes down to we're doing these things to try to make this kind of weird kernel more efficient, and that the methods that we're applying become more apparent when we have it smaller and even less efficient.
Okay, there's a question, what is your target total GPU count, and do you anticipate scaling issues?
So that's a really good question. So we work hand in hand with some of the scientists who have developed and who use this code for their work. So I don't know exactly what is in mind for their target goals individually. We're looking at more of a supercomputer-esque goal in the end, especially when you take into consideration the higher resolution from the DKIS telescope. I wouldn't have an exact count, but I would say we're definitely looking in the realm of running on like a larger supercomputer, ideally. And do I anticipate scaling issues? It's hard to say. We're working in a much smaller scale right now. We're working within Casper, and we're starting to get up towards like 8, 16 GPU, and we're already doing a bunch of debugging and stuff. So right now it's hard to say, but probably there'll probably be some issues to work out. Could you explain a little bit about the layout, how it affects the performance? So this would be like how you decompose the problem across the multiple GPUs. So like it's like 2 by 1 by 1 versus 1 by 1 by 2. They're both 2 GPUs, but splitting the problem up differently. The main difference between how we decompose it, for right now, since we're only working within a single node or possibly 2 nodes, we're working with a fairly small amount of GPUs. So when we say 2 by 1 by 1 or 1 by 1 by 2, the performance difference between the decomposition is going to be more relevant than if we were on 100 or 1,000 GPUs, for sure. Some things to keep in mind right now while we're still kind of at this scale is that the 3 dimensions, they're going to be X, Y, and Z. The Z direction is typically our innermost loop. So for GPUs, a lot of times you want that loop to be a decent size for vectorization. So if you split too much in like the Z direction, for example, that vector loop's going to get smaller and that could hurt performance and things like that. And there's also other kinks we're working out, like how communication in like one direction is giving us slower performance than another, and we're still figuring that out now, but that's like profiling and development stuff. Do you want to give that, so this is coming from my advisor, thank you. Do you want to give the audience an idea on how we dealt with correctness of the code for the CPU and GPU? So what we're doing now is we have essentially a Python notebook that generates a few numbers and a few plots. So we have run the code in several configurations on a CPU with different kind of CPU decompositions. And we've recorded the output of MURaM at different time steps. Normally we do it in increments of like 10 or so. And what we do is when we run a GPU version, we will essentially record the output at the same time steps and compare them, compare their numerical output. And we have a threshold of what we're looking for. So a 36 CPU core run, we don't expect it to produce the exact same results as a single GPU run. And that's mostly just because of things like RT integration has to do a bunch of communication and things like that. It's not going to get the exact same answer, but they should be similar. So essentially what we do is we have a reference, we run it on the GPU, and then we have an automated script that plots it and everything for us to show us if we ever blow out of our threshold. And that is fancily automated at this point, so that anytime we do a commit to the Git, it runs and emails everyone a sad report if the commit fails. Yeah, thank you for the question.
Okay, so I guess I would ask you if you have a sense of what the, from what you're seeing, what the optimal basically chunk of sun per GPU is for the current state of optimization. What's your sense of that? So
like essentially per GPU?
Yeah, like number of points on a side, or, you know, the patch size, if I could say it that way.
Yeah, I think it was interesting when I was doing the different versions of Integrate to see how it differed based on the size. So it's entirely possible that the most optimal version is maybe with a smaller data size to get more benefit out of Integrate. One thing we haven't really measured, which has to be considered before we commit to that, is how the smaller size affects the rest of the code. Because while it might be really efficient for RT, if it hurts everything else to a very significant degree, there might be some trade-off we have to consider. So it's definitely hard to say, but I hadn't considered the possibility that going as small as like a 64 cube or a 128 cube was going to be optimal, but it's very possible from what I've seen so far.
Is it possible that the aspect ratio is also an issue? So like pencils as opposed to cubes, if I could put it that way.
Yeah, it certainly could be. I don't think we haven't really sat down and dealt directly with how much of an impact it is. But one of the things that we definitely do know is that how you decompose it will determine how often, like for example, how often you get a Z dependency pattern in Integrate, and that could definitely hurt performance. But we haven't really measured in a significant way how to determine it yet.